Good morning. Thank you for joining us on this lovely, Wednesday morning. I would like to introduce our friends from Gravity 9 and the NHS, who are going to be speaking to you this morning about the adverse event classification for medical devices. I'm not going to read the rest of that title. I'll let them do the explaining. So, gentlemen, take it away.
Thank you, Oliver. Good morning. I'm Eric from Gravity 9, and we are a software modernization company with a focus on MongoDB. Pleased this morning to share a story about how we've been using AI along with our clients, Guy's and St. Thomas Hospital, to potentially improve health outcomes where something maybe has gone wrong in a medical procedure. We're very excited this morning to be joined on stage by Didi Akinluyi, the Chief Biomedical Engineer at Guy's and St. Thomas Hospital, as well as Loghman Zadeh, the Head of AI at Gravity 9. What we'll do today, first I'll introduce Didi to tell you a little bit more about the problem, why it's an important problem to solve, and sort of why there's such a focus on it, and then hand over to Loghman to give you some ideas about how AI helps to impact this problem, why it's relevant to that, and give you a demo of the solution that we've built using MongoDB Atlas on Azure. So without further ado, Didi, over to you.
Thank you. Thank you very much, Eric. And good morning, everyone. As Eric told you, I work at Guy's and St. Thomas's. I'm one of the leads there. And as part of the NHS, and a big part serving South East London here, we have a lot of scrutiny on us. We have lots of room for improvement, and particularly around what we do with our data. So I've been working with Gravity 9 for a couple of years now on a platform to transform the way we adopt medical technologies, the way we learn, and the way we convey those insights more broadly. And this is one of those aspects. So adverse events. In a hospital, we have this obligation that we should report everything, including near misses, and we should be learning. Just like in airlines, every report must be logged and learned, or should be, let's say. And in a hospital like mine, which is one of many in London, we will have something in the order of 50,000 of those events per year. And some of those, if they're medical technology related, I have them sort of streaming through my phone almost. What we want from that data is to be able to mitigate things locally. We also want to be able to feedback learning to the wider system to say if there's a problem with the product, we need to know now. Other hospitals need to know as well, and the regulator needs to know. So normally what happens is when something goes wrong, nurse or doctor, it would be great if they were using a handheld, often they'll go to a workstation later and they will type up a free text report to understand what has gone wrong. And that will go into a local risk management system. And a more recent development is that we're aggregating that across the NHS, so those free text reports are going into a learning from patient safety events database. And the idea is we can trend, and we're looking at currently at the free text to try and understand which issues emerge. Thanks, Loghman. And there are lots of different stakeholders. I've told you about the local mitigation, that we want to fix an issue in our own hospital, in our trust. There might be a system-wide issue, there might be a product issue that needs to be dealt with, and our regulator, the MHRA, is very interested in this data. Not only does it mean making things safer, but it means, for example, if a groundbreaking new technology comes to the UK and we say we want to adopt it, we want to generate insight around it, we can take that technology sooner if we're monitoring and we're confident that we can capture incidents and respond to them. So it's a driver for innovation as well. But the problem is, at the point of capture, the data can be poor, and we're not sharing that laterally. It's all very vertical. So if I wanted to learn about what's happening in London, if there's a cybersecurity issue with a device, I won't necessarily know until it's gone all the way up and come all the way down sometime later. So we've been thinking about how we can improve the depth, quality, and shareability of that data, and that's what I've been working with Gravity 9 on. And I think at this point, I can set out the issue that we have with categorization. So from a device manufacturer perspective, they actually have internationally a set of codes, generic codes, which they would say classify any issue with. And there are around 500 of these in one dimension, and there are 7 dimensions. So you can see an example of this on the slide. You can see that there's a hierarchical structure, and actually, to some level, even osseointegration problem is quite vague for some applications. But the problem is, at the point of reporting, people reach for the free text. Any coding happens post hoc. So how would we describe what goes wrong? well, currently, if we wanted to use that coding and make the data more tractable, it would be with great difficulty. So in this case, a gastrostomy tube has been blocked for some reason. There are a number of codes which you could apply, but the idea that a nurse, doctor, another healthcare professional will search through the 488 codes and actually encode the data is just not going to happen. Or that even they would get to the level of detail we want, and that's our problem. At the point of capture, the data isn't good enough. So this is where we see one part of the opportunity is, can we improve that classification? Can we improve practice at the point of entry? Therefore meaning that it's easier to capture, we capture more, better data, and we can respond for patient safety more. And I'll pass over to Loghman to explain some of the concepts that we're looking at.
Thank you, Didi. Hi, everyone. So, as Didi explained, so in fact, to solve the problem of the classification, we take the embedding concept, which is the base concept, to somehow create a latent space and use the similarity search to find out the most similar codes to the adverse event report. Generally, as a high-level architecture for the system, from the left side, we took all the information related to the standards, which is IMDRF, and we try to use the embedding model to store all the vectorization, vector version of the categories inside the MongoDB Atlas vector. And from the right side, when events happen, so the clinician try to enter the events to the system and passing that one to the retrieval component to create a embedding of the adverse event report text, and then using a similarity search and retrieval component, we use the MongoDB to retrieve 20 similar categories to the adverse event, and then using a ranking algorithm, we pass and retrieve only 5 top categories with the similarity score. So with the base RAG or retrieval augmented generation approach, we couldn't achieve a good accuracy and performance. But I will show you in the following slide further improvement. But at the bottom of the diagram, you can see there is a extra part in a pink arrows. So we took also the adverse event report, we passed the adverse event to LLM to extract the name of medical device and the related components, and then storing them alongside the assigned category specifically to extract more insight. And this is a sample visualization of those insights. The pink circles shows the code, and the green circle shows the component and the devices. And simply we can find the relation between different codes and component and understand the accuracy of the or the performance of the system. So to improve the base RAG solution, we took another step, and it was using a HyDE or hypothetical document embedding. In fact, instead of creating embedding directly from the adverse event report, we used an LLM to generate a hypothetical document. This hypothetical document, in fact, explained the category that should be assigned to this adverse event. And then we use this hypothetical document for similarity search. So as an example, number one is the input adverse event. It is showing, it explained the, showing the crack after multiple cleaning of the device. The target category is A21, which is related to the deviation from the documented specification in the product catalog. And the generated HyDE document or hypothetical document is somehow try to explain the category that should be assigned to this adverse event. And it increase the quality of the retrieval generally. Another step that we consider to improve this process, from the left side, you can see when we took the categories, in fact, the first level of this categorization or code, the description was so short and we couldn't really find the best matches. So what we did, we concatenate all the description of the subcategories, and using an LLM, we generate the summary of all the description and assign this summary to the first category, which helped a lot to improve the quality. And from the other side, when we received the adverse event report, we generated the hypothetical document, passing the same process and retrieving the 5 top categories with their similarity score. As a result, so we achieved almost 78% accuracy using our testing dataset, which was include around 2,500,000 examples, and somehow we managed to get a very good accuracy in some categories. At the same time, you find generally there is some problem with the regulation and the definitions of some of the categories that the regulatory body, they need to revise and maybe refine the problem. So from here, we will switch to a live demo and play a video to show just how this process works and how we created the system. It is a simple demo. So as you can see, instead of writing the code on the left side, we have a multiple option. We select one of these options, one of the adverse event reports. So in this case, the report is about, I think, somehow the target category should be A04, which is a material integrity problem. And we can see some of those reports is very short and so difficult to categorize them. So using the base embedding model, I think we try to retrieve, but we have more improvement. As you can see on the checkbox, we can use the hide and also adding the summarization. But without selecting those options, we can see for some category or adverse event report, we can return the categories properly. And in this case, A04 is the first recommended category. So it depends on the quality of the report. Sometimes the system would struggle to propose the best solution. So this is another example. The expected category is A05, and it explained that 6 hill room over bed needed some sort of repair. This is the general, I think, problem that explained. And without any using of the improvement, so the basic retrieval augmented generation process couldn't retrieve the proper category. But by including the summarization of all the subcategories to the first category, we try to check the result again. And again, I think there is a difficulty to retrieve the right category in the list, as you can see. And finally, by generating the HyDE or hypothetical document, we could achieve the proper accuracy in the process of the retrieving related category to this adverse event report. So that shows how the process of the improvement or different step can help to increase the accuracy of the AI system, specifically RAG applications. So generally, I try to show more, I think, examples in the video. But from here, maybe I will stop and take the time to get some questions. Meanwhile, thank you for listening, first of all. But if there are any questions, any thoughts and feedback, yes.
Hi, can you hear me? Can you hear me?
No, unfortunately, I don't have. Yeah. Exactly. Yeah. Okay. So generally, HyDE is a technique to generate hypothetical document. So instead of using the original description of the adverse event report, because everybody has a different style, different type of writing, different type of way to explain the event. So instead of that, we used an LLM, and using the prompt engineering, we asked the LLM to explain the category that could be assigned to these adverse event reports. So the input of the LLM was the prompt that asked the LLM to generate or explain the IMDRF category that could be assigned to these adverse event report. As a result, the LLM generate a hypothetical document that explains what is the problem that could be assigned, what is the category that could be assigned to that adverse event report. And we use the embedding model to embed these hypothetical document and search inside the embedding space instead of embedding the adverse event report directly. So it increased the quality of retrieval because the description of the hypothetical document is so close to the categories that we had in the embedding space. Hopefully it makes sense. Brilliant.
Hello. I'd like to ask about this process.
Yeah, sorry. No, you can also speak to. Yeah.
All right. About this process, it's so small, so short text. When you send to LLM, when you get the response,
Yeah.
how do you make sure you don't have any hallucination happening? Do some sanitization on the data? Do double check? How do you make sure there's no hallucination coming back from the LLM? So what can mess up the result?
Exactly. This is a great question. So how we can try to prevent any hallucination when we get the hypothetical document. So generally there is different techniques. In this case, what we used, in fact, try to rely and check using a testing data set, check the hallucination scores for the whole data set. And in fact, because it is some sort of prompt engineering process, you need to have a really precise prompt to get a proper result. We check, and the quality of the generated hypothetical document generally for our solution was quite good, and we didn't need to do anything. So because it wasn't impact the specific part of the solution, it was just try to help to improve the retrieval part. And also we had the re-rank process in the retrieval part, so to improve the quality of the retrieve list or the recommended list to the user. But there is other techniques. Also, you can use generally some sort of guardrails to prevent the hallucination and calculate the hallucination score as well. Yes. Maybe because I need to listen as well.
I saw you had a confidence score up there.
Yeah.
How well calibrated is that? And like, you know, if it says 70% confidence on there, will that be the right category 70% of the time?
Okay, that's a great question. Exactly.
And how did you generate it?
So that one, in fact, we try to calculate the accuracy of the system. We mentioned 78%. We retrieve 5 type categories. And if the right category was inside the 5 retrieve category, we calculate that as a correct answer because we retrieved the right one. At the same time, we calculate the misclassification or misrecommendation during the process. And as I mentioned, some of the categories we found out the description of the category is really vague. It's so difficult for human also to assign the category. Specifically, there was 4 specific category with their subcategory that the definition was so close to each other. And it highlights improvement from the regulatory body to somehow improve the definition of those categories. So this is the way that we try to generally calculate the accuracy score. And if we use a standard data set, as I mentioned, 2,500,000 samples for checking the quality of the system. In fact, this is a standard or real-world example that has been collected by FDA, and we use that data set to evaluate the accuracy and also performance of the system. Hopefully, I managed to answer your question. Is it?
I was wondering particularly about the confidence score that comes back in the JSON.
Yeah.
So when you were doing the demo, there was a confidence from, like, maybe is that
Exactly.
from Mongo? Or?
Oh, yeah, that's the score, exactly. The similarity score, it was the similarity score between the description of category with the hypothetical document or maybe the adverse event report. So we used the similarity score for that one. And as I mentioned also, we had the re-rank algorithm, which tried to go through the retrieved data from the MongoDB. At the beginning, we retrieved 20 examples, 20 top examples from the MongoDB, and with the re-rank, we break down to the, come down to the 5 top one. Yeah. Brilliant. Thank you very much.
Thank you very much for those great questions and your attention. If you'd like to continue the conversation, please join us on the Gravity 9 booth. Loghman will also be participating in the AI Build Together event this evening for any of you who want to sort of get hands-on with AI and work with Loghman on that. Thank you to Didi and Loghman as well as yourselves.